Okay, welcome back. Quick topic today, energy efficiency. All right, so we've talked about efficiency a little bit before. We brought it up in a lab, and I introduced the symbol that we use for efficiency, which is the Greek letter eta. And here's how I write eta. It's like a lowercase n, but instead of stopping, I continue the tail down with a big long swoop that goes below the baseline. So this is not a symbol that you are expected to know or recognize, okay? It's a new symbol. This is eta. It's a Greek letter. I think it makes an I sound, all right? We use it to denote efficiency, which the book defines as the desired output over the required input. All right, I think this is a pretty good definition. It's the one the book uses. And so notice that this is talking about any system at all. It could be a specific machine. It could be a method of transporting energy. It could be a method of storing energy. It could be a method of converting energy between forms. Anything like that we're talking about, this is a very general idea that the efficiency is the output over the input. And so the way I sometimes remember it is simply the shortcut version, E out over E in, okay? Energy out over energy in. It's pretty simple to remember. It's also pretty intuitive. Now, one other way that you might see this written is if I write the energy out as the energy in minus an energy loss. Hopefully you can see why that's the same thing. I could just rewrite the output like this, and then on the bottom I have still energy in, and then this is then equal to 1 minus E loss over E in. Okay, so this is an alternate way that you might see it written. Energy loss over energy in, 1 minus, all right? So the other thing we can do is we've been talking about energies, so this could be fill in whatever you want, work, heat, anything like that. Those are forms of energy. We could also write this in terms of power, all right? Imagine that I took this expression, E out over E in, and I want to multiply it by 1 in a convenient way. So I'm gonna multiply top and bottom by a time interval, delta t. That changes nothing about the expression because it's the same factor on the top and bottom. But we recognize that this, the energy over delta t, that's an expression for power, all right, which we denote as W dot. And then this one is the reciprocal, okay? So we can write this as the power out over the power in. And you've seen me use that trick before, where I change an expression about energy into one about power by multiplying or dividing by an arbitrary factor. So it's really not changing it, it just looks like it's in a different form, okay? So this is an expression having to do with power. Okay, so what I'd like to call your attention to is that when people talk about efficiency, I think I'm spelling that right. When people talk about efficiency, they're using colloquial language, right? Like an everyday term, you hear people that know nothing about physics using the word efficiency. So I want to formalize exactly what we mean when we say efficiency. Because one person might say, oh, what's the efficiency of that? The other person will say, oh, the efficiency is this. They're not speaking the same language. They're using the word efficiency in 2 totally different ways, but they might not even know it. So I'm adding this. You'll not find this distinction in the book, but this is really helpful as you research and hear about this stuff for the rest of your life. Understand that the word efficiency is used in 4 different ways, all right? So let's say that this is a machine. It can be anything, but a machine will help us get some examples, all right? The first type of efficiency is a universe limit, okay? I'm spelling stuff wrong today. Universe limit, all right? Now, as you may have guessed, the universe limit, no matter what we're talking about, is 1. Now, where do we get that from? It's obvious if you think about it in terms of the conservation of energy. Imagine that I had an efficiency that was more than 1. That means that the number on top is more than the number on the bottom. That means that I've created something, some machine, that outputs more energy than it inputs. And if it outputs more energy than it inputs, well then, I've created a machine that is creating energy out of thin air, all right? That would be a problem. And so the maximum efficiency that we can have for any machine is 1. And that is a limit set by the universe, all right? It's a fundamental law that cannot be violated. Now, you may ask, okay, well, I've heard of efficiencies less than 1 though, and so you just made an argument based on the conservation of energy. The energy can't be created or destroyed, but if the efficiency is less than 1, well, is energy being destroyed? Where's that extra energy going? Notice that the definition had the desired output over the required input, okay? The key is desired output. We, when we put energy into a machine, only get back some of that in terms of what we want it to do. The other energy is wasted. So think about a car engine. We put a certain amount of energy in, that's our required input, and what we get back is we want the car to go down the road. We want it to accelerate, all right, and overcome the force of friction to stay at a constant velocity, or even if we're speeding up. So that's our desired output. So the energy that goes into that car is leaving the car in the form of some, what we want it to do, and some that we don't care about, like heat and waste gases and stuff out the back. And so that energy is not being destroyed. That's not what we're saying with an efficiency of less than 1. We're not saying any energy is actually lost. We're saying that it's going a different direction than what we desire. All right? So, universe has a limit of 1. The next type of efficiency that people talk about is a physics limit. All right? And I want to write in parentheses here the word supertask. Now, I would highly advise that if you want to really understand what I'm about to bring up, the idea of a supertask, YouTube a video called Vsauce Supertasks, okay? He does a really good job explaining what these are. But this is the idea of a physics limit, all right? And this is a theoretical thing that you can even think about doing, but you can't do in practice. So let me give you an example of a simple supertask, and you're gonna have to believe me that this is true, because you won't have actually seen this mathematically unless you've taken Calc 2. That's where you would deal with this. So if I have a block that is 1 inch thick, all right? And then I take another block that's 1/2 inch thick, and I put it on top. Then I go get another block that's 1/4 inch thick and put it on top. And I keep getting blocks, and each block is half the thickness of the block before it. So the next one is an 1/8 inch thick, then a 1/16 inch, then a 32nd of an inch thick. And I keep stacking these blocks. Now, here's where the supertask comes in, the part I can't really do. I stack blocks an infinite number of times. Now notice that this isn't actually possible in the real world. That's what differentiates a physics limit from the next one we're going to talk about. A physics limit isn't really achievable, but we can think about doing it, because here's the result from calculus. If I were to stack those blocks an infinite number of times, I would not get a stack that's infinitely tall. I would get a stack that's exactly 2 inches tall. All right, let that break your brain a little bit. Spend some time thinking about it. But I can give you a result. My answer is not infinity. My answer is a finite number, 2 inches. But can I ever really get there? No, because it requires an infinite number of blocks. And if I'm stacking them, it requires me to have an infinite amount of time. Okay? So that's the idea of a physics limit. It sets up a bar that we can try to go up to, but never quite get there. We're gonna ever get closer and closer and closer, but there's this hard limit that we can never cross, all right? The next type of limit is an engineering limit. And this is something that we can actually do in the real world. And this is not like a hard boundary. This can fluctuate. It can go up and down based on technology improving. So this is essentially saying, in the real world now, how good can we actually build a machine? What is the best machine that we can currently build? And this is always going up, because as technology keeps improving, we're pushing and pushing and pushing these limits. All right? And the third one, or the fourth one that I'll add, is just practical considerations. And these also fluctuate up and down. So I'll tell you in a second what I mean about practical considerations, because I want to just use 2 examples. So I hope you can read this. The first example is going to be solar power. Example of like a solar cell, all right? So our input is energy from the sun, and our output is electrical power. So of course we have a universe limit of 1. We can't create energy in solar cells. We have a physics limit of 0.87 efficiency, all right? That means that 87% of the sunlight could be converted into energy, but there's a catch. This 87% comes from a calculation of a supertask. So, for example, just to give you a flavor of where this comes from, we start with a stack of solar panels that are infinitely tall. Okay? And then we deal with a light source that is infinitely bright. Okay? So there's a lot of stuff here that is not actually achievable, but we can think about, what if we had this? And if you do all those calculations, you get an efficiency of 87%. It's the absolute theoretical limit, but it's not reachable. So the reachable limit is about 47% efficiency right now. As of last year, this is the world record, okay? 47% efficiency. And then our practical limits are things like conditions, price, and size, right? So we can only build realistically solar panels that are so big, and we can only realistically have them cost so much to make, because our materials can't be like the best in the world every time. And certainly with solar, if it's cloudy or if it's at night, then we don't have any efficiency at all. So if you average over the course of a year, you're going to get something well below the peak efficiency of a solar panel. And so most solar panels on a practical level that you go out and buy, those are about 15% efficient, okay? Those are just practical considerations. And so there's these 4 different numbers that are kind of efficiency limits, but they depend on what you mean when you say efficiency. My other example is going to be wind energy, so a wind turbine. The universal limit is, of course, 1. The engineering or the physics limit is 0.59, and yes, this is another super task, okay, to actually get to that limit. So we can think about it, but we can't quite get there. Engineering limit is currently about 0.47, which I just realized that's the same number. And then with practical considerations, most solar farms right now are running at somewhere around 40% efficiency, just practically, okay? So that's kind of important to remember, that we have these different types of efficiency. So I'm going to pop back to this board to talk about the very last idea, which is when you have multiple efficiencies in a system, how do you add them? Now note, I'm going to say adding efficiencies. How I do it mathematically is I multiply them. We do the same thing with probabilities. If you have two probabilities and you want to know what is the probability that both of these come true, so what is the sum of these probabilities, what you do is you multiply them. It's the same with efficiencies. If I want to know what's the efficiency of my machine plus the efficiency of my storage unit, what I do is eta total equals eta machine times eta storage. Okay, I multiply the two numbers to add them. I say adding, and I do multiplication. I know it's confusing, but this is actually how this works, all right? So let's say, for an example, that you had, you were looking at an energy system, like let's say a solar or a wind farm, okay? So from a wind farm, how would the energy get to your toaster? You'd have to add up all of the efficiencies. So first, the actual wind turbine, what's the efficiency of the machine, then what's the storage, then this energy needs to be converted, there needs to be an electric generator, and I'm going to say converted 1 because it needs to be converted into electricity. Then there's the efficiency of the transport system to transport the electricity to you. Then there's the efficiency of the conversion to, okay, because once we transport the energy to your toaster, we have to convert it back into radiation energy so that you can radiate your toast. And then there's the actual efficiency of how much of that does your toast absorb, so how quickly can it cook. So I could add that on. And so all of these different efficiencies in the chain are required to get the actual power from the wind into heating up your bread to make toast. And I can just keep adding on the terms here by multiplying them, okay? And every time, since these etas are all a little bit less than 1, every time this number is going to get a little bit lower, okay? I'm never going to be able to put something in this chain and multiply and make the total bigger. I'm always going to get lower. And that's why we add efficiency.